Hi, I'm Gary Rubenstein, and this is part 15 of my series of videos taking you from kindergarten math through trigonometry. And I've been teaching math for 30 years, and I was a math major in college, and math is my hobby. So I have a lot of thoughts about these different topics, and I just want to collect them all, and I hope that it helps some people to understand math a little bit better. Now, in part 8, I did geometry for elementary school, which had some properties of like triangles and area and perimeter, and it ended with pi. So this video, and probably the next one also, because geometry is a full year course, so I think it's probably worthy of 2 40-minute videos, but we'll see how this goes. Part 8 ended with circles and pi, and before I get into some details, I just want to tell you, like, we spent a year on algebra first, then most schools do a year of geometry, and then they do a year of algebra 2, and then they do something called pre-calculus, which is kind of like algebra 3, and then calculus. Some schools do geometry before they do algebra because you can interchange those as far as when you learn them. Geometry over the years has changed a lot as to what we mean when we say geometry. So back, way back in like BC times, when geometry was basically being discovered and invented, Euclid wrote a book called The Elements. And Euclid, we're talking about the year 300 BCE, wrote a book called The Elements. And it's a pretty long book. It's about 700-800 pages, separated into 13 chapters. And in there, the goal of that book is to find properties of various shapes and to slowly build up these properties until, and to be able to prove that the properties are true. So it's not just about, oh, here's a formula for perimeter and area, but like, how do we know that this works? And it is very, very sophisticated. And people have been studying those books, The Elements, for over 2,000 years. They're very highly, printed. Some people say that besides like the Bible itself, it's kind of like the Bible of math. It has been in continuous publication since BC times. And if you're an adult and you remember geometry and the proofs, it was really, really complicated and confusing. Nowadays, a lot of the geometry is not what's called proof-based, but it's kind of informal, like you mess around with shapes and see what properties you seem to be true about them, and then we memorize, formulas and things about geometry. So it's kind of like there are a lot of schools that still do the old school geometry where you learn how to prove things, and then there's sort of the new school, which is sort of less formal. And some people think that we need to go back to the old school because geometry was not so much about shapes, but about what sorts of things can we build from like a limited set of tools. And some people think that limited set of tools in doing proofs is way too old school, and it's doesn't really serve like a really great purpose anymore. We have so many other things that we can think deeply about that that are also worthy of thinking about, and the idea of like proving things about shapes maybe isn't so relevant in today's world. I want to give you a taste of both sort of schools of thought. This is going to be the hardest 2 videos of the entire sequence of videos, I can already tell. One of the things that people study in geometry is a fact about triangles. So here is like a random triangle. And a triangle has three sides, of course, but the name triangle is not tri-side, but it's triangle because it has three angles also. And there's different kinds of triangles. If all three angles are equal, it's called equilateral, and if two angles are equal, it's called isosceles. This one has three different sized angles. And we make these marks sometimes. If they had the same measure, I would make like two of them, but they have different measures. So those are the angles. I'll stick some letters here, A, B, and C. So we have angles A, B, and C. Now, an angle is a kind of abstract idea. I mean, we have the general idea that the letter V forms, an angle. And there's like skinny V's, and there's wide V's. And the skinniness or the width of these V-shaped things are measured in degrees. A degree is like a really skinny V-shaped thing. And if I take those things and kind of try to see how many, if I lay them side by side, imagine like a pizza slice. The number that fit inside, more of them fit inside this angle than fit inside this one. When you put 90 of them together, you get what's called a right angle, which we recognize because a square or a rectangle has those four nice right angles. Right angles is a sophisticated concept. The idea of like perpendicular lines, that two lines can cross and be perpendicular if they make a nice square corner, whereas if they're crossing like this, it's not a square corner. So this is four right angles, and this is not four right angles. But even showing little children, here's a rectangle, and then you give this thing and say, why is that not a rectangle? And even a little child might say, well, the corners are not square or whatever it is that they want to say. So they have an intuitive feel for like right angle versus not right angles. Angles that have less than 90 degrees are called acute angles. And angles that are more than 90 degrees are called obtuse angles. These two angles, A and B, definitely seem to be acute angles. Though that angle C is hard to say. It might be obtuse, might be a little bigger than 90. Might be a little less, might equal 90 degrees. There's no way to know just from looking at this picture. Let's say that I measured these three angles and found out that this one was 100 degrees and this was 50 degrees. Is there a way to figure out what that third angle is? Well, the answer is yes, and it's based on a somewhat surprising theorem in geometry. A theorem is like a rule, but a rule that someone has like proved using some of the tools of geometry. And I'll get to what those tools are in a minute. But I'll tell you what the theorem is, that the three angles of a triangle, of any triangle, add up to 180 degrees. So if that theorem is, if it's true, which it is, and this is 100 and that's 50, then the third angle would have to be 30 degrees because 100 plus 50 only adds up to 150, and I would need 180 So if I do 180 minus 150, I would get the missing angle. Now, this is surprising. It means no matter what triangle, I could take a triangle like this, make a little tiny triangle with 150, and that angle would be 30 also. And any triangle in the world, here's 20, 150, that would make this guy have to be 10. So this theorem is something, it says the word any. Every triangle in the world, no matter how, as long as it's drawn on a flat surface, we're not going to get into spherical triangles right now, non-Euclidean geometry, but any triangle that you can think of as a triangle it's going to be true that the three angles add up to 180. That's something, we can't say that about perimeter. Like, it's not true that the three sides add up to anything. You could have big triangles, you could have little triangles, but no matter what triangle I make, the three angles have to add up to 180. And that is something that people memorize. And then on a test, teachers will ask a question like this. And a student who knows that the three angles add up to 180 can add up the two and see, if I got into 180, how much more do I need to get to 180? But that fact about the three angles in a triangle add up to 180, is that really that important of a thing? Is that worthy of studying? Like, it's interesting, and we can answer questions with it, but why do we need that? Why would anyone care that the three angles add up? Is there ever any time in life that you have a triangle and for some reason you really need to know what the third angle is and you know the other two? No. So why have we been studying this for 2,300 years and learning this as one of the most important things? Well, what's important about it is not so much the fact that the three angles add up to 180. But the reason people study it so much is that it's something that we can prove is true. Something that we can prove is true for all triangles. I mean, I could draw millions of triangles and test it over and over, but that doesn't mean that it's always true. What if someone finds a triangle where it's not true? Then it's not a theorem anymore. It's not anything anymore. So we study geometry as this almost philosophical thing of what things can we prove have to be true, in this case, about every triangle that's ever been drawn and every triangle that ever will be drawn. Now, nowadays, a lot of times they don't do a formal proof of it, but they might do an informal proof. So they might have kids draw a bunch of triangles, and then they notice that and then make them do a chart and say, do you notice anything? And some kids will say, oh, I noticed that in every triangle, when I measure the three angles, with a protractor, they added up to 180. There is use to that because that's called a conjecture when you think it's true, because when you test it for a whole bunch of triangles, it's a conjecture, and a conjecture could be true or false. In this case, it is true. So how does someone prove something like this? I just want to give you a flavor for it. Well, they have to use certain tools. And in geometry, it starts with just a few basic tools. Like, for instance, in the old school geometry, there's only 5 what are called postulates. And then there's a bunch of things called common notions. I don't want to get into all those right now. I think I want to say that one of the tools is that if you put 2 right angles together, they make a nice straight line. And that means that if you have an angle that's so wide that it basically becomes a straight line, we would say that's a 180-degree angle. Now, if you take a straight line, that means, and you put a point on it, and you draw a line in any direction away from it, these two angles will add up to 180 degrees. So if this is 50, you'd be able to figure that that one's 130. If I take a straight line and I put a point on it, and from that point I draw two more lines like that, it produces three angles. This one, and this one. And at this point, all we can say for sure is that those three angles add up to 180 degrees because they're like a jigsaw puzzle. They make that straight line. So to make this more concrete, I would go like this. I would tell students, if this is 30, and this is 7, and this is, let's say, 40, what's that third angle? And they'd have to say, okay, well, 30 plus 40 is 70, so I would need 110 degrees. If I don't know what those angles are, all I could really say is that those three angles add up to 180 degrees. Now, before I get to the proof of the sum of the three angles in a triangle add up to 180 degrees, I'm going to show you like another simpler proof. If you take two lines and they make a big letter X here, and if I told you with one of there's four angles in this picture, if I told you one of them is 40 degrees, and I asked you, can you find the other three angles? Well, you could, because here's a nice straight line. So this 40 together with whatever this angle is has to be 180. So that has to be 140 degrees. And now if I take this line, I'll make it red. This red line is 180 degrees, so this 140 means this guy has to be 40 degrees. And this green line here is composed of this angle and this one. So that angle has to be 140, because those have to add up to 180. So with the letter X, we see that the angles that are sort of across from each other are always equal to each other. When you have the letter X, angles across from each other are called vertical angles. And in this case, if I told you this was 40, you could calculate that that other angle is 40 also. And the theorem is vertical angles are always, I'll use a fancy geometry word, congruent, which is a fancy way for saying same size. We don't say equal because that means they're actually the same thing. So you could have two people that are the same height, but that doesn't make them the same person. So we use the word congruent. It sounds like just a fancy word for equal, but it's a fancy word for like same size. So the way a proof works, I'm going to call this angle 1, 2, 3, and 4. So I want to prove that if I have this picture, that the angle 1 and angle 3 have to be the same size no matter what. Informally, I would say, okay, well, if angle 1 is 40 degrees, prove that angle 3 has to be 40 degrees. And you would say, well, angle 1 and 2 have to add up to 180, and angle 2 and 3 have to add up to 180. Therefore, they're both 40 degrees. But a proof is more general than that. This is just a proof. This is just a specific case where there's a 40-degree angle formed by that x. So the way a proof looks is you go like this. You say, I don't know what the measure of angle 1 is. I don't know. I'll just call it measure of angle 1. But I do know that angle 2 and 1 together make a straight line. So measure of angle 2 is 180 degrees minus whatever the measure of angle 1 is. Because this red line forms 180 degrees, these two angles together, 1 and 2 add up to 180. So whatever angle 1 is, angle 2 is, measure of angle 2 is 180 minus measure of angle 1. Now now let's forget about angle 1 for a second and look at angle 2 and 3 make a straight line. So we can say that angle 3 and angle 2 have to add up to 180 also. So I can say that angle 3 is 180 minus whatever angle 2 was. But angle 2 itself was 180. Here, let me write this. It's 180 minus measure of angle 2. But we've established that measure of angle 2 is 180 minus measure of angle 1. And then you could take this expression and you could write it as 180 degrees minus 180 degrees plus measure of angle 1. That part you may need to go back to another video. If we're subtracting something minus something, we say sometimes we distribute the negative through, but more so if you're subtracting 180 minus something, it's the same thing as subtracting 180 and then adding in the extra thing, because you're basically you're taking away something smaller than 180, so you have to add back. And then the 180s and 180s cancel out, and you just get measure of angle 1. So that's a long way to go to prove that. But that proves that it's true, not just when angle 1's 40 degrees, but I don't know how all that stuff came back. But that proves that it's always true, no matter what. I got to erase this now. That's what a proof looks like. And I'm not saying that this proof blows you away, that angle 1 and 3. But that's what's meant. That's geometry. I mean, long time ago, in Egyptian times, geometry was just a practical thing that you just learned formulas for different shapes, find the area, and things like that. But it turned into, in Greek times, this sophisticated thing where it was all about what sorts of things can we build from limited tools. So this vertical angles are always congruent came from very limited tools. It just came from the fact that a straight line has a 180-degree angle. The fact that vertical angles are always congruent is not such an important thing. You can get through life perfectly fine. First of all, it might be kind of obvious to you. You can almost see there's a line of symmetry here. You can almost see that without proving it. But that's what the proof looked like. I showed you that proof just to give you a feel for what they mean by proofs. Because now what about the theorem, the three angles, of a triangle always sum? That's a harder thing to prove. In order to prove that, there's something about geometry that I want to just tell you and not prove it. When two lines are like this, they form what are called parallel lines. And when you draw a third line that cuts across it, it's called a transversal. But more importantly, it forms the letter Z. Now you could have a Z that's like this, or you could have a Z that's like that. The only difference in these z's, or you could have, you could have all kinds of z's. The thing about z's is that the top and bottom are parallel. And the thing you might notice about the z is that there are two angles in the z. And without proving it, but it is something that in geometry they do prove, those two angles will always be the same measure. And they seem to be. I mean, it wouldn't look like much of a z if I had like an angle like that, and then this one was like a skinny angle. Seems like the two sides of the z, the top and bottom, wouldn't be parallel anymore. In geometry, we say if the lines are parallel, these are called alternate interior angles, but they'll always be congruent. But informally, it just doesn't look like a z if these things aren't the same measure. It seems like as long as these two lines are parallel and I connect this to this, I'll get congruent angles here and here. I'm not going to prove that there. It's going to say, that seems to be true. Let's accept that. Now we can come back here. So here is a triangle. Just a random triangle. And I have these angles, angle 1, angle 2, and angle 3. Why should they add up to 180 degrees? Well, if I draw in another line, and I make this line parallel to this base here, then I get, see this green from here to here to here? I get a letter Z, which we saw before. I'll leave this as black. That means this angle and this angle part of the Z, so I could put angle 1 there also. And you may not think of this as a Z, but you know when little children draw their Z's, they sometimes make them backwards. I used to do that with the letter D and P. So there's a backwards Z. Well, that rule before is also true of backwards Z, so that means this angle is equal to that angle. And now we can see up here, this looks very much like the picture I drew over here. Those three angles up here add up to 180 degrees. We don't know what they are individually, but them together creates this straight line, which is 180 degrees. And that means that the original angle 1, 2, and 3, which are the same sizes as these angles 1, 2, and 3, also adds up to 180 degrees. And that proves that it's always true. And again, you may not think that that's like something that's worthy of proving something that's always true. You might think it's enough to just memorize, like trivia. Here's a fact. The angles add up to 180 degrees. But unlike other subjects where we memorize facts, the Revolutionary War started in 1776. You don't prove that. You memorize that. That's a thing that happened. But in math, there are things that aren't just trivia that you memorize. But what makes it math is that you can prove those things. And it's the proofs, which sometimes we don't even teach anymore. That's why math has been a subject for all these years, because they decide, they felt it worthy of doing these proofs a long time ago, and we just keep doing them. Again, it's arguable whether it's really worthwhile to prove things. And that's why when I make my other geometry videos, I'm not going to be doing proof after proof. I mean, a geometry course is a year-long thing that takes hundreds of hours where you prove theorems one after another. But I just wanted to give you a feel for that's what geometry at least was until maybe like 15 years ago when they started making geometry a little more informal. Geometry was about proving things like this, and then using this thing as a tool to prove a more complicated thing, and just going until you prove, really complicated things. But that's all I want to say about this video, believe it or not. All I did in this video is more like philosophy and tell you what the story with geometry is. And I proved two things. I proved that vertical angles are congruent, which again is probably not a big surprise. They look, if I draw a letter X, these two angles look like they're both congruent, and they are. And that in a triangle, the three angles have to add up to 180 degrees. I had to cheat a little bit and just kind of tell you that let's just accept the fact that the angles in a Z are equal to each other, or congruent. Anyway, there'll be another video coming next with a lot of different theorems in geometry that I think are important for us to know, but this video is about what is a proof, why do we bother doing proofs, and begs the question, if the proof isn't important, is it even, certainly the fact that the angles add up to 180 can't seem to be that important of a thing for real life. What's more important, the proof of it or the fact of it? Because I would argue the proof of it is more important in this case than the fact of it. So if the proof isn't important, the fact isn't important either. And why do we bother making kids memorize that the sum of the angles in a triangle add up to 180 degrees? Maybe it is something worth, just knowing, just because we could ask questions about it, but you could get through life just fine without knowing that the sum of the angles equals 180 degrees. And you could get through life just fine without knowing how to prove that the sum of the angles equals 180 degrees. But if all you did was memorize that the sum of the angles is 180 degrees, that's trivia. That's not math. Math is logic and using some rules to figure stuff out. In algebra, that's the ways of solving for x, but in geometry, it's proving theorems. Geometry is proving one theorem, and then using that theorem becomes a tool that you could then, once it's proved, to use in a more complicated proof, and then you just keep going with that, and there's no seemingly end to it. Okay, this was a very odd video. It's geometry part one, because I'm really realizing that there's got to be at least 2 parts, and maybe 3. See, don't give up on these. You could skip to the next one, and there's going to be more stuff like the other videos. But I just needed to say this since geometry has been taught for so long, and Abraham Lincoln carried around Euclid's Elements with him, and it was not just about memorizing a fact, but about the process of logically, proving something.